Great. Thank you for the introduction, and I'm really excited for this workshop. I think it's such a great topic and it's been central to a lot of my research over the last few years. I wanted to begin, though, by questioning why we're all here and just ask the question, what is the point of 3D reasoning and geometry in deep learning? I think the story that we've all been told again and again over the last few years is that end-to-end deep learning destroys any other method that we can come up with today at so many tasks. And here I'm showing a plot of ImageNet performance over the last few years, and you can see that progression in end-to-end deep learning has been unparalleled by any other method, and has largely caused developments in being able to build very powerful representations for image recognition has largely driven a complete disruption in the field of computer vision. And it's not just computer vision, so if you think about a lot of these complex data science fields, you'd almost be laughed at if you didn't use deep learning. Everything from image recognition to speech recognition, NLP, protein structure prediction, or some complex control tasks. Deep learning end-to-end deep learning is really the prevailing method. And most likely you would be laughed at for doing something different. So the paradigm is that we have a ton of training data, we have a giant neural network, and we try and learn an output, often with supervised learning or with whatever learning that you prefer. But it's quite remarkable how well this method generalizes and how widespread it is across understanding all kinds of different data. So I'd make the claim that if we have sufficient data, enough modeling capacity, and a good enough optimizer, then end-to-end learning is best. We just want to learn from input to output, right? And if we have a reasonable amount of data, which we often do in many of the problems we work on, if we have enough modeling capacity, I'm not talking about an infinitely deep neural network, but a 100-layer residual network is often enough. And we have a good optimizer, SGD, or some of the more interesting optimizers that we have out there with some useful loss functions. This is usually the recipe for success, right? And I don't think anyone in this room would disagree with me so far. Do shout out if you do. So that begs the question. And to me, what is the point of computer vision? Because as a roboticist, computer vision is all about extracting a representation of the world which we can use to make a decision, which we can use to understand the world and make an action with. But I've just presented a narrative to you that end-to-end deep learning outdoes pretty much any other method you can think of. We want to learn from input to output. So why do we need computer vision? If computer vision is all about getting a representation to make a decision, but we're seeing the prevailing technology today relying on end-to-end learning, so why do we need to reason in 3D? Why can't we just go from input data to control policy, or input data to localization? Why do we need 3D geometry? Why do we need computer vision? And what is the point? In fact, why are we here today? What is the point of modeling geometry and problems that involve 3D structure? Can we not just learn this end to end? So this is something that puzzled me for the last few years, and I guess this is the direction the field is going. And as computer vision researchers, what is our role in the world when work is going more and more towards the paradigm of end-to-end learning, of black box optimization, of learning directly from perception to decision or perception to action. So I want to present a narrative today of my take of this problem, and maybe motivate where I think some of the key research questions are going to be over the next few years, and how they've influenced my work over the last few years in computer vision. So first of all, I wanted to show you a demo video. This is something that I put together with my team up in Cambridge, and this is a demonstration of what happens when you do learn end-to-end in robotics. So this video is a end-to-end learning system that takes an image as an input and outputs control commands for a reinforcement learning vehicle. So it outputs directly from image to driving commands. And it's initialized from scratch. It knows nothing about the world. It just takes random driving actions. And each time it makes a mistake, or tries to drive off the road, the safety driver intervenes. And so you can see that through this random driving and random intervention, it's exploring and learning about the world. And we train this with reinforcement learning, with the reward to try and drive as far as it can each time without the safety driver taking over. And so you can see after a few pieces of training data, it can't drive, it just tries to crash. So we keep training it. And this model initially knows nothing about the world. It doesn't know what physics is, doesn't know what a road is. But you can see with this reward, it incrementally learns how to drive. And now after, I think, about 5 pieces of training episodes, you can see it learns somewhat unstable, but it learns to slightly correct, and it can swerve back and forth. And you can see it's learned to correct when it gets to near the edge of the road, but ultimately it's still unstable. And after a wee while, you'll see it, again, tries to crash. So what do? We keep training it. We give it a bit more data. Now this was the first time anyone had ever put reinforcement learning on a real-life physical mobile robot or a self-driving car like this. And you can see that after only 11 episodes and pieces of training data, this car is able to learn how to lane follow. So that's what end-to-end learning can do, right? So if we can learn from scratch, from knowing nothing about the world, to being able to drive without computer vision, that begs the question, what is our role as computer vision researchers? So that's the narrative that a number of people in this world are telling, and in fact I have told. But now I want to tell you the real secret as to how this works. And maybe this will motivate why computer vision is important. So this algorithm that we put on the car was effectively a modified version of something called deep deterministic policy gradients. This is a reinforcement learning algorithm popularized by our friends at Google DeepMind, and it was designed largely for solving continuous Atari games or simulation problems. And they typically train it with, in the order of millions, sometimes hundreds of millions of examples of data in simulation to be able to solve some video games, for example. Now, I just showed you this car learned to drive in about 10 episodes. So how do we get from the data efficiency that they need in simulation? We have perfect information, privileged information about the world, like the distance you are from your lane and things that you get from simulation. We have all that and 10 million training examples. How do we get it down to learning in just 10? Now, the answer here is computer vision. It's learning a representation which we can use to make a decision. In fact, the way that we got this to work, and to do this with such efficiency, is as well as this reinforcement learning loss, we also had an auto-encoding loss that tried to auto-encode the image from the car down to just 2 dimensions. And then it was trained to decode it back to the image in an auto-encoding fashion. Now, what these 2 dimensions, we realized we needed 2 dimensions, because when you auto-encode an image of this road down to 2 dimensions, you learn 2 things. The lighting of the scene, so whether it's a sunny or cloudy day, and the second one is the position of the road. Those are the 2 dominant features in that image. And so we had to use computer vision techniques to compress that megapixel input image down to 2 dimensions. And then on those 2 dimensions, the algorithm, deep deterministic policy gradients, could learn to drive in 10 episodes. If we tried this algorithm on the raw driving data, it just wouldn't work. So maybe that illustrates why computer vision is important in end-to-end deep learning. So if we go back to this claim and the statement that I made at the beginning, let's pick apart a bit. We often don't have sufficient training data. Especially in real-world problems, you're never going to find a test set that equals your training set. Do we have enough modelling capacity? Well, ResNet can't model everything. You can't build an infinitely big, dense neural network and train it. We can simplify it with convolutions, but 2D convolutions and residual connections, they aren't going to model everything in the world for us. And what about optimization? Well, often supervised learning isn't enough. We can't get enough of a training signal out of this. Or reinforcement learning might be very sparse for us. So how do we, how can we improve this, and how can we do better? And as I mentioned before, for me, I understand computer vision, and in an extension, geometry and 3D reasoning, which is what we're talking about today, is all about how we can build an efficient and effective representation to make decisions. Now, these 2 words are key, because efficient, computer vision can help us make these things faster, more computationally efficient, more data efficient at learning. And effective, we can improve performance by increasing the quality of the training signal, the quality of the representation. And so that's what it's all about for me. And today I'd like to spend this presentation talking about how I've used these ideas and how 3D reasoning and geometry has helped some of my research in designing end-to-end deep learning methods for building representations in stereo vision, localization, object detection, and scene understanding. I hope that motivation was clear, but does anyone have any questions before I kick off the technical work? Please interrupt if you do at any stage. Fantastic. So I'd like to begin to talk about stereo vision. So again, the reason why I've chosen this to begin with is it illustrates quite a clear narrative about what I'm trying to explain. So stereo vision, as most of you will be aware, is the problem of taking two images, in this case rectified stereo pairs, and trying to determine the disparity between them. So you can think of disparity if you have an object nearby you and you alternate closing your left and right eye, you'll notice that this object moves in space, and that's known as disparity, and it's inversely proportional to depth. So here I'm showing the two left and right input images to a stereo algorithm, and down here is the depth prediction, or inverse disparity prediction, and on the right is also the uncertainty prediction, which is something I won't talk about today, but this is also interesting because you can see that the depth prediction can be uncertain at areas around occlusion boundaries, around homogeneous areas like the sky where there aren't many features, or very confusing textured images with lots of ambiguities like in the foliage or the leaves. But I'd like to talk about the geometric aspect of this problem today. So what is the history of stereo vision? So stereo vision was first taxonomized, well, it's typically taxonomized into four key parts. It's all about, or traditionally all about building out features, producing a cost volume, regularizing that cost volume, and then estimating disparity. And this is how the research predominantly was developed over the last few decades. It was about solving these sub-problems in order to estimate disparity from two rectified stereo images. So when deep learning came along over the last decade, we've seen it start to move more and more towards end-to-end. So initially, there was some work that took over the matching problem. So this was being able to learn the matching costs with end-to-end deep learning. And then over time, more and more work has progressed to end-to-end deep learning, in a very naive sense, perhaps, where you simply take an encoder-decoder architecture, and with that kind of initial naive approach, learning end-to-end, and it gets pretty good performance. It's more efficient than state-of-the-art, and it's comparable in terms of accuracy. And so this was the initial, first attempt at throwing end-to-end deep learning at this problem. So what this illustrates is that throwing a naive end-to-end deep learning method, just an encoder-decoder at stereo vision, gets us pretty far. But what I want to talk to you about next is an architecture that I worked on during my PhD, which tried to take that naive end-to-end deep learning model and see, can we, if I go back a slide, can we bring in more of the ideas of geometry and 3D reasoning to improve this? And how can we use computer vision to improve the representation we get? So you'll note that a key part of this problem was all about forming the cost volume and being able to reason in 3D. And so part of this work, and it was putting together a neural network that we can train that is able to reason in 3D. And it turns out we can do this with differentiable layers and 3D convolutions. So just to explain this architecture, which was termed geometry and context net, this architecture is all about encoding each image through some convolutional filters, some 2D convolutional filters, and then taking those feature maps and producing a cost volume. So a cost volume essentially takes these are 3D tensors, so we have a height by width by feature tensor, and we look at the cost of displacing that tensor at different intervals with the other image, producing a 4D result. So we have a cost volume which is height by width by features by disparity. And we can produce this through simple concatenation, addition, subtraction, splicing operations, which is all differentiable. And so rather than just encoding and decoding an architecture with deep learning, what we do here is we explicitly form a cost volume with the ideas that we know about 3D geometry. We now have this 4D tensor, which we can convolve on in 3D, so we can convolve across the height, width, and disparity dimensions. And we can convolve this with 3D convolutions to do more, to reason and understand and filter this tensor before running a differentiable soft argmax operation. And so this is an example of an end-to-end deep learning network that uses our knowledge of geometry and 3D reasoning in order to improve performance. And it turns out that this ends up surpassing those naive approaches and the traditional hand-engineered approaches, and tells a nice story about how we can use geometry and 3D reasoning to improve our end-to-end deep learning networks and make them both more effective and efficient. Does anyone have any questions about this work on stereo vision? Fantastic. So I'd like to move on to a second area, which is in localization. So this is actually the problem that got me into computer vision. When I moved to Cambridge about 5 years ago to start working on a PhD, I was absolutely awed by all of the 3D reconstruction work that you could do at the time. You could download an open source packages. I walked around Cambridge with my smartphone taking video and produced some amazing 3D reconstructions. And this actually is what inspired me to move into computer vision. And I thought it was beautiful looking at all the architecture in 3D. One of the first projects I worked on was the problem of localization, initially from a SLAM perspective. But I've been reading a lot about how deep learning especially disrupted the area of image recognition, and thought, again, why can't we throw an end-to-end deep learning network at this problem? So I did that. I collected a data set of images and their corresponding camera pose through structure for motion around Cambridge, and trained an end-to-end deep learning model to be able to regress camera pose. And so this network, which we coined the name PoseNet, was trained in an end-to-end fashion, taking an off-the-shelf recognition network to learn from image to camera pose output, trained with a loss function that just minimizes the metric distance between the predictions for position and orientation and the ground truth position and orientations. And so this system was completely naive, throwing a black box neural network at it, and performed reasonably well. One of the key results for me was seeing that it could generalize to test data, and not just, as some people suspected at the time. They thought that neural networks were large piecewise linear functions that did a lot of very efficient nearest neighbor matching. Maybe they are, but what this work showed was that they could actually learn a smooth manifold. And you can see here, some of the training data is in green, and so you can see the manifold, well, the sequence of the training data of poses along the street. This was me walking around with a smartphone taking very unorthodox photos down the street. But then if you look at the blue, the test sequence, which is taken in often different weather, different days, different time, and certainly different spatial locations like here, you can see that this neural network was able to learn to interpolate, and was able to learn a smooth manifold that generalizes to novel camera poses. So I was excited by this because it was evidence that we can learn geometric reasoning and we can learn geometry with an end-to-end network. But it still didn't perform as well as some of the traditional methods. So again, this is where the story comes back to how can we use geometry to improve these systems, and how can we, well, one of the key problems with the system was the loss function. Learning to minimize camera position and orientation is very noisy. It requires optimization in the camera space, and we know from structure for motion that the way we typically do solve the problem of jointly optimizing camera position and geometry is with bundle adjustment techniques, is with optimizing in feature space in 3D through reprojection error. And this is something that we know from work in the field for many decades. So we reasoned that can we apply this to in a learning setting as well. So what we did is we then designed a loss function which, rather than minimizing the error in camera position space, can we minimize the error in projection space? So if we take our ground truth orientation, position, and geometry. And the prediction from our network, we take the predicted camera pose and geometry and put it through a projection function. We can project this 3D data to 2D and look at the reprojection error here. And that naturally combines the errors of position and orientation, and turns out that that's able to give us a more accurate localization estimate. So when we look at the results, the naive PoseNet model was able to localize to about 2 meters error and 6 degrees in large urban scenes to around a city block scale, and a similar error within small indoor room scenes. But when we bring in this geometric loss function and start looking at the reprojection error, it can improve performance by up to 70%. And so this is again trying to repeat the story that we can do better than just throwing a naive end-to-end deep learning model at the problem, but we can use these ideas that have been studied for many years in a feature engineering sense, but use the power of deep learning to learn to combine the information, to do sensor fusion, to learn to extract features in a better way using a differential network that learns to optimize directly for the data set that we're working on. So that's really the benefit, and sensor data and improving performance by reasoning about context and geometry, which I'd encourage you to read more about if you're interested. The next area I wanted to talk about was in monocular 3D object detection. And this is some more recent work that's currently under review, and it's on arXiv if you're interested, and it's been led by one of my colleagues in Cambridge, Tom Broderick. And I'm really excited about it, so I thought I'd also spend some time diving into it here. But this is the problem of trying to reason about objects in 3D, and in particular, the problem of taking a single monocular input image and trying to predict each object in the scenes. For example, here, each car's position, orientation in 3D, and also their height, width, and depth. So you can see here, taking an input image and predicting this 3D bounding box is the problem I'd like to talk about here. So typically today, this is there are two main lines of research here. One is in image-based systems, which I'm going to focus on here, and the second is in LiDAR-based systems. LiDAR-based systems excel because if you have a range depth sensor, you can get absolute depth. The geometry is more observable from the scene, and they're much more accurate. And this is shown in the benchmarks. If you look at the most popular benchmark, or one of the most popular benchmarks here is the Kitty 3D object detection benchmark. And these are some of the scores of 3 LiDAR methods and 3 vision methods, and you can see there's very little comparison. When you dive into this, you can start to look at what the metrics are actually measuring, and they have a very tight tolerance on error. And so if you start to look at more of robustness metrics or recall metrics rather than precision, then it's a little bit of a different story, but ultimately these LiDAR methods, as expected, perform significantly better. So if we look at the image-based approaches, what are the key challenges here? Well, unlike LiDAR, as I mentioned in the image-based approach, we don't get absolute measurements of depth. There's also a large variance in scale, so cars can be 200 pixels high, they can be 2 pixels high. There's a very large variance here. Viewpoint also matters, so we've got perspective projection and distortion that doesn't exist when you reason in 3D space. And finally, the space is non-metric. So if you think about pixel coordinates, because of perspective projection, distance in pixel space does not equal distance in metric 3D space. So it's very hard to do 3D object detection. So I'd like to talk about an idea we had in some work of how to address this and how to actually improve these 3 problems with monocular 3D object detection. So this work really revolves around, again, improving the representation. How can we improve our representation of the world in order to solve these problems? And how can we use geometry to make this better? And so the key approach we took here is to move away from a perspective projection space and an image space to an orthographic space. So you could think of this like a bird's eye representation. If you think about the bird's eye view of a road scene, this is an orthographic world. There's no perspective projection. There is metric space. There's no major scale artifacts because things are equally spaced out. It's all metric and it's in absolute depth. And so the key part of this, the key motivation for this work is to address these problems that I identified about depth and scale and non-metric space with moving to orthographic space. And again, we're going to do this with end-to-end deep learning. So, I'd like to introduce today and walk you through what we call the orthographic feature transform. So like I said, we want to use insights of geometry and this idea that I presented of using orthographic bird's eye view representations to be able to reason about objects in 3D. So how do we do it? Well, again, we want to encode some features from this monocular image and then project it to this orthographic space. So now we're talking about voxels. So 3D voxels that we can represent the orthographic space with. And then we can reason about it in 3D, similar to the method I presented in stereo vision, where we can do 3D convolutions and finally end up with a bird's eye view that we can regress the 3D object positions, orientations, and sizes. Now, the key thing here, which I'd like to focus on, is how do we project from 2D features in image space to 3D features in orthographic space representing voxels. And that's what I'd like to talk about today, and that's what requires a bit more of a deep dive into representations of geometry. So how do we do it? Well, this is the problem, right? We want to go from image features to voxel features to bird's eye features. What the idea we came up with was to take these voxel features and project them into the image, and we can do this through perspective projection. And you can see each voxel represents a different region in the image. So then if we pull those features, we reason that those features from that area correspond to that voxel. And so by pulling those features, we can form that voxel representation. And then, of course, as I described, we can do 3D convolutions on these voxels to give us a bird's eye representation and reason about occlusion, height, and filter the space. So if that makes sense, we can use various forms of pooling and perspective projection from 3D space to be able to form these representations. Now, one of the questions is how do we do this efficiently? Because when we first implemented this in the lab at Cambridge, it was very inefficient and blew up in terms of GPU memory. Here's why. If you think about how many different pooling features you need to do to go from voxels in the order of 250 millimeter voxels, so that kind of area of space in a 30 by 30 meter region to an image, this is how many. It's about 460,000 pooling operations. Now, if you compare that to a common object detection network like fast RCNN, which does this in 2D space, it only has to do about 2,000. So this difference in order of magnitude makes this very slow. And one of the key problems we had to overcome was how do we pull this efficiently? Again, this narrative goes back to traditional research in geometry, and one of the concepts we identified and learned from was the seminal work from Viola and Jones about summed area images, and about trying to use some of the ideas that came out from this research in to be able to build the orthographic feature transform. So what Viola and Jones showed in this paper from when was it? From 2001, was how to pull features very efficiently. So what they propose is creating an integral image. So an integral image is the idea that if you sum across rows and columns of an image, so you can see if here's your image, and you create an integral image which sums along each row and column to create a cumulative value of that pixel. So that's an operation you can do very efficiently in a parallel sense on a GPU. You can then do much more efficient pooling, where you don't have to operate over each pixel within the pooled region. You can simply, if you want to pool over this area here, there is a for example, if you want to pull here, then you can simply take the vertices of each of this pooling region and sum the A and D vertices and subtract B and C, and that will give you the value of the cumulative pooling of that region. And that's very efficient because you no longer have to do a sum operation over that area. Instead, you can just use this much more efficient concept to be able to pool more efficiently. When you're thinking about moving to the scale of the pooling operations you need to, this was absolutely essential. So does that make sense about this idea that we want to project the 3D voxel to a 2D image space, and then we want to pull the features there to build our representation of that voxel, and the way we do that efficiently is with these integral images. So that's the core idea behind the method, and turns out this is very powerful because what this lets us do is we can create a voxel representation, which has the benefits I described earlier. We can reason in 3 dimensions. We remove the problems of perspective projection and absolute depth, which have plagued monocular methods, and this is the kind of performance that we obtain. So you can see this is a video from the test sequence on Kitty, which is the benchmark that we worked on. And this is what our method predicts in terms of 3D object detection. Now, one of the qualitative conclusions we can draw is that our model performs much better than prior monocular methods at reasoning about objects far away. This may be because our method reasons in orthographic space, whereas in perspective projection, objects that are very far away are very underappreciated in terms of convolutional features. We also get more accurate orientation estimates, and again, this may be because we moved to this metric space, this 3D space, and can reason in 3D to form this object detection. And you can see we also get metric results of depth, and so this is showing the top-down representation I talked about and what our model predicts in terms of locations of different cars. So I thought this work was particularly relevant today because it shows how we can improve on naive methods. The very first monocular 3D object detection methods of deep learning just simply took a masked RCNN model, a model designed for 2D object detection, and tried to get them to regress 3D object coordinates. This is again an initial naive approach, and what we were able to show is that by using geometric ideas and reasoning in 3D, we can outperform prior state of the art. And you can see by the results on the Kitty data set that this was the previous monocular state of the art, which we outperformed considerably, and we get close to the metrics of a stereo method, which has explicit depth information. So that was particularly exciting to us, that reasoning in 3D and geometry can give us that kind of level of improvement in performance, and perhaps begin to approach some of the methods in stereo. It's still a long way to go to LiDAR, but it's a start. One of the most important results in the paper was looking at the 3D reasoning part of this network, which maybe this is a big takeaway for the audience today. If you think about the network I presented, what I'd like to show here is two curves showing the performance if you remove or ablate the size of the 3D reasoning network. So you remember we take image features from either a ResNet 18-layer or 34-layer network, project them into voxels, and then we have 3D convolutions that reason over these voxels in order to produce our 3D object estimates. Now you can see if we remove that 3D reasoning, we get incredibly poor performance. And even if we move to a bigger front end that reasons in 2D, so we move from an 18-layer to a 34-layer ResNet, the performance doesn't increase very much. But when we start to bring in 3D reasoning and 3D geometry with 8 layers or 16, you can see this is where we see a massive performance improvement. And the performance goes from a very small amount, about 1 in terms of our 1% in terms of our error, up to where the benchmark was about 9%. So this, what this ablation study shows is that the power of this network is predominantly in 3D reasoning.
Alex, you said error rate for that vertical curve. Do you mean precision rate?
I believe the metric was looking at, it's a precision metric for intersection of union. So bigger numbers are better, and it's intersection of union of the 3D bounding boxes. It's quite a tight threshold, but bigger numbers are better. So in the interest of time, I'd like to just skip over the scene understanding work and just finish by talking about some of the more recent applications of these ideas in autonomous driving through a team I'm leading and working with in Cambridge. So we go by the name Wave, and what we're really trying to pioneer and work on is trying to bring more intelligent decision making to robotics to produce more safe, trustworthy, and intelligent systems that can reason with end-to-end deep learning. And I think one of the largest and most impactful technologies for our generation is going to be self-driving cars and autonomous mobility. And so we're focusing on building out technology for self-driving cars. And I'd like to share how some of the ideas that I presented through my research in computer vision are driving this technology. I just want to quickly share where self-driving is at in the world today. So there has been billions of dollars of investment, largely in China and the USA, producing self-driving technology, which predominantly is based on methods that rely on hand-coded features, and in particular on mapping, on lots and lots of different sensors and hand design rules. And this, I guess, very much goes away from the approaches that we've been seeing in the research field about how end-to-end deep learning can give us more powerful representations. But today, everyone is focusing on these three main forefronts, and it's not working, right? We're only seeing very limited trials of self-driving cars in places like Phoenix, Arizona, where you have sunny weather, wide boulevards, and it's almost the perfect world to test these vehicles. So what are we trying to do about that? Well, if you look at how computer vision technology is going and the rate of development, this is showing the difference between the beginning of my PhD and the end of my PhD. This was a network I worked on called SegNet, which was one of the first to take deep learning and apply it to the problem of semantic segmentation. And this is something we were very excited about at the time because it started to generalize the entire world, and we built a web demo where people would upload images from all over the world to see how it would perform. But if you look at where we are at now, we don't only understand semantic segmentation in a far more nuanced way that's more accurate and fine-grained, but we can also understand depth and motion. And so when I was introducing this talk and talking about computer vision, and my motivation for computer vision is all about building representations to make decisions and actions. This is an example of where we're at today with our technology. And I believe this is driving our ability to make actions with representations from computer vision. Because if we can understand semantics, geometry, and motion, then perhaps that's what we need to be able to drive. Maybe we can move away from reliance on these maps and these rule-based systems that some of our competitors are working on. So that's what we're doing at Wave, and I can show some initial videos of our system. We have vehicles that are driving around in Cambridge with end-to-end deep learning, relying on technologies like imitation learning and reinforcement learning, driving completely rules and maps free, learning entirely through data. And this is how we believe we're going to get vehicles to scale. So this is something I'm super excited about, and draws on a lot of the ideas that I've been talking about so far in this presentation. So these are some of the side streets in Cambridge, and this is our vehicle driving completely autonomously down these streets using just computer vision. To show you some more results from the vision front. So this is, again, our system driving, and I'd like to show this representation of semantics, geometry, and motion that's powering this system. And you can see that the systems we build can be very robust and generalize to, certainly to Cambridge at least, but that's, that's really what's motivating a lot of this work. Again, I think one of the key takeaways is that if we just simply try and do what the machine learning community is proposing and simply learn end-to-end from perception and action. We've tried that, these systems don't work. How we really get this stuff to scale is to use 3D reasoning, using semantics, geometry, computer vision losses, and building these representations. And it's, I think, the computer vision community that is going to enable, the computer vision community, I think, is going to be pivotal in enabling data-driven control methods for robotics to move from the realms of simulation to real robots, because understanding this high-dimensional complex data that you need to in the real world needs computer vision technology. By putting all these ideas together, we've been able to show a couple of things, and I want to highlight some of the ones that I'm most excited about. So I showed you a video at the beginning of this presentation, which is the first time reinforcement learning or deep reinforcement learning has been applied to self-driving cars. And so that's what computer vision and end-to-end learning can enable. The second one I just want to quickly show is a sim to real problem. So this is a problem of training and simulation. So you can see here we have a cartoon world. And can we train in simulation and take this technology and put it in the real world? One of the big problems with simulation is it looks very different, right? It's a different visual domain from the manifold of natural images. And it's been a long studied problem about how do we take things we learn in simulation and put them in the real world. So what we went about doing here is, again, trying to build a representation with computer vision that allows us to do that with end-to-end learning. So we took the idea of a cycle GAN and tried to use image translation techniques to apply a model that we train in simulation to the real world. And we showed for the first time a self-driving car that's been trained only in simulation with no real-world training data that can drive on the real roads of Britain. So this is the first time this has been done, and this is a car in Cambridge driving, and it's trained entirely in simulation. It's never seen any labeled training data from the real world. And as I mentioned, it uses a cycle GAN to encode a latent space that is shared between the sim and the real domains. And that's how, using these computer vision losses, we're able to build this representation. So if I just skip to some of the results at the end, you can see that this is how we're able to achieve zero-shot sim to real performance, is with computer vision technology. And that's why I encourage that even in the realm of end-to-end deep learning, computer vision is absolutely critical. So I'd like to conclude with a few thoughts on what I think is next, and these are some of the things I'm personally very interested in and I'm pursuing in my research. So if they interest you too, I'd love to chat about them this afternoon. If you'd like to work with me or collaborate with me on them, I'd also love to talk, because they're things I'm very passionate about at the moment. So the first one is video. I think today a lot of these end-to-end representations for decision making are very much constrained to single images. We see single image depth prediction all the time. We see semantic segmentation. Understanding motion and being able to predict the dynamics of a scene is something that I think is very understudied at the moment. And that's an area that I think is going to be key, and it's maybe the missing building block in some of the representations I've been showing you, from geometry, depth, localization. But what about motion and scene dynamics? And I think this comes from video. Video is a great source of self-supervision that we've seen over the last few years, and I'm very excited about extending these ideas to video, and I think that's one of the next frontiers for computer vision. The second one is memory. I think a lot of the work, first of all, memory is a key part of intelligent systems. I'd happily make that assertion. But I think, again, this is where state-of-the-art research has fallen down so far. I think a lot of it today focuses on question and answering systems in natural language. And that's maybe where the fire is burning in research on memory systems and machine learning. I think 3D geometry and SLAM is a really fantastic setting for this research, and I'd love to see more work come out of SLAM, because SLAM is such a great setting for memory. It requires localization and spatial memory, which I think, and you can do this all without labels, right? You can do it through self-supervision. So I am very excited to see and work on applications of or understanding machine learning-based memory using 3D geometry. And the last one, which is a particular focus for me at the moment, is on combining perception and action. If perception is all about developing a representation that we use to make decisions, how do we combine these systems together? A lot of the research we're seeing in robotics and control, for example, in manipulation robotics, in solving video games, and the game of Go with reinforcement learning, this all just, these systems have an observable state of the world, it's often low dimensional. But if we want to move to real robotics, we need to be able to combine computer vision and machine learning for control. And this is an area that's very understudied as well, in my opinion, and I think it needs a lot more effort. One of the things that I've been thinking about more recently is, and actually discovered, better performing models on computer vision benchmarks, like if you get a model that has a better intersection over union metric at Cityscapes or Kitty or one of these popular data sets we work on, that doesn't necessarily mean a better self-driving car model. We're starting to get so good at a number of these different metrics that they are no longer proxies for the indecision task. And one of the things I believe quite passionately is that I think we need to look at the computer vision systems we build in conjunction with the application that we're trying to work on. So endlessly optimizing intersection over union or endpoint errors in these models, I think is becoming more and more fruitless as we approach increased performance. I think we need to look at more at robustness, modeling uncertainty, and providing the right signal for how to drive. We don't care about segmenting the clouds and the trees. We care about self-driving, the scene right in front of us. And that's what I think combining perception and action can help us with. Great, so I really enjoyed presenting this material, and thank you very much for your attention. I'd be happy to take any questions.
Thank you very much, Alex. That was really great. Next, we have some questions from the speaker.
The projection and